In this video, we will look at the algebraic definition of even and odd functions. So as a reminder, an even function is one that has symmetry with respect to the y-axis. So if you take a function and reflect it over the y-axis, you will have the exact same original function. An odd function is symmetric with respect to the origin. That means that if you take the function and rotate it about the origin, you'll have the same original function, or you can think of it as a double reflection. If you reflect the function over the y-axis and then the x-axis, you will get that same original function. If neither of those criteria are met, then the function has neither symmetry. So let's look at a little visual to begin with. This first function has even symmetry. It's a parabola. If I reflect it over the y-axis, it's the exact same shape. If I find the value of f at 2, it's this coordinate right here, and it is equivalent to 4. F at negative 2 is this point here, and it is also equivalent to 4. So we can make a general statement that f at 2 is the exact same as f at negative 2. And this, if we generalize it, applies to all even functions. F at x is equivalent to f at negative x. And if we think back to transformations, this makes sense for even functions because that negative is in the place of the k value. And if our k value is negative, that means we have a reflection over the y-axis. So we can reword this as saying the function f at x is equal to the same thing if it's reflected over the y-axis. And that is what makes it an even function. Let's look at an odd function. Here we have a base function for the cubic, x cubed. This has odd symmetry because if I were to take the point at the origin and reflect this around function, that origin, over the y-axis, or it would look if I reflected the function like this over the y-axis, I might have something like this. But if I reflect it again over the x-axis, then I'll go back to my original function. So now let's look at f at 2. F at 2 is equivalent to 8. F at negative 2 is equivalent to negative 8. Now how can that negative 8 turn into a positive 8 if I multiply it by negative 1. So we can make a general statement that f at 2 is the same thing as taking f at negative 2 and multiplying it by a negative. And that leads us to this general statement. A function will have odd symmetry if f at x is equal to negative f at negative x. As a reminder, this outside negative is the a value, so there's the reflection over the x-axis. And like we said before, this negative is a reflection over the y-axis. So if you have two reflections and you end up with your original function, that has odd symmetry and it's an odd function. And if both of those criteria are not met, it is neither. So let's look at a few examples and test this out. We're going to determine algebraically if each function is even, odd, or neither. And I'm going to start off by testing for even symmetry. If I reflect over the y-axis, will my functions match? Now, with function notation, we know whatever's inside the bracket will replace x. So I'm going to replace x with negative x. And now I just have to clean this up. A negative number to the power of 5 will be negative. So negative x to the power of 5 will be negative x to the 5. Negative x to the 3 is negative x cubed, times the positive 2 is negative 2x cubed. And then minus x. These are clearly not the same thing. F at x does not equal a reflection over the y-axis. So now we can conclude this is not even. So now let's test for an odd function. And since we already have f at negative x, I just have to take that expression, here it is, and multiply it by negative 1, which means I'll just distribute that negative in. And that will give me x to the 5 plus 2x cubed plus x. And this is the same as the original function. So f at x equals negative f at negative x, making it odd. Let's try the next one. Let's test for an even function. So replacing all of my x's with negative x. And this time I have negative x to an even exponent. A negative number to an even exponent will be positive. So negative x to the 6 is positive x6. Negative x squared is positive x squared. They match right away. So h of x equals h at negative x. So if I take my function and reflect it over the y-axis, it will be the same as the original h of x. This makes it even. And next one, g of x. Let's test for even function first. Turning my x's into negative x's and cleaning up. So negative x to the power of 5 is still a negative number. Negative x cubed is a negative number times the 2 makes it negative 2x cubed, and then plus 1. These are not the same thing, so it is not an even function. So let's test for odd. So just taking that original g at negative x, putting a negative out front, and distributing that negative in, which will just change all of the signs. And when it does that, this still doesn't match because the ones are the wrong sign. So g of x does not equal g of x when it's reflected over both axes. So it is neither. Now I want to do another example or two where you're given a function in factored form. So for example, let's say we have a function f at x equals negative 2 x minus 3 squared and x plus 3 squared. So I'm going to test for even first. Okay, so I'll change all of my x's to negative x. Now, please ensure you do not try to distribute that 2 in because that is not proper distribution. Some people might be tempted to write the bracket out twice and do distributive property. Although that could get you to the correct answer, it is time consuming. So what I would do instead is factor out a negative from each of the brackets, these two. So when I do that, the negative x minus 3 will turn into x plus 3, and the negative is out front, which remember is like a negative 1. And each of these elements, the negative 1 and the bracket, are raised to the power of 2. And then I'll do it again. So factor out a negative, or if you want to see it as negative 1, you're more than welcome to. And that will turn it into x minus 3, all to the power of 2. Now the negative 2 is not affected. And now, remembering your exponent laws, for example, if I had a times b to the power of 2, we know that we can distribute the exponent to both terms because those two terms are multiplied. Now, our two multiplied terms here are the negative 1 and the bracket. So we're going to distribute that in. So we would have negative 1 squared and x plus 3 squared. Negative 1 squared and x minus 3 squared when we distribute the other. And now, time to clean up. Negative 1 squared is positive 1. No need to write that. Negative 1 squared again, still positive. No need to write that. And now if I compare, yes, my brackets are in a different order, but the order of multiplication doesn't matter. So these do, in fact, match. So f at x equals f at negative x, making it an even function. Let's try one more. Let's do g of x equals 3 x minus 2 times x plus 1 cubed. So I'll test for even first. So that'll be negative x minus 2 and negative x plus 1 cubed. And I'll factor out the negative. Now here, for this first bracket, when I factor out the -1, there's no exponent on top, so it's just out and about now. But for the next one, when I factor out that -1, it will be raised to the power of 3. So here, 3 times -3 is -3, just going to clean that up. And then here, when we have -1 to the power of 3, that's going to be negative, and then x minus 1 to the power of 3. And then I can clean up the -3 times the -1, that's positive. Now, if I compare my functions right now, they are not the same thing. So I will try negative g at -x. And all that's going to do is add a negative in front, which will not fix anything. And please keep in mind, since this is factored, we're not distributing this negative in. They're already attached by multiplication. So if I were to try to, let's say, distribute the negative into this bracket and into this bracket, I have now multiplied by -1 way too many times. So I put it out front. This implies multiplication, so there we are. These are not the same thing either. G of x does not equal -g at -x, and it also does not equal g at -x. It is neither type of function. It's not even or odd. And that's it for even and odd symmetry algebraically. So once again, an even function, if you take the function and reflect it over the y-axis, they match, which means f at x should be equivalent to f at -x. Whereas with odd symmetry, you need that double reflection for the functions to match. So a reflection over x and y-axis, which means f at x is equivalent to negative f at -x. And that's it.